We can divide the reagents that oxidize alcohols to carbonyl compounds into two classes based on the strength of the reagent. So-called strong oxidizing reagents, or strong oxidations, convert primary alcohols, which contain two hydrogens linked to the alcohol carbon, all the way up to carboxylic acids. And this is two steps up the oxidation ladder, from +1 in the alcohol to +3 in the carboxylic acid. Secondary alcohols, which have the general formula you see here, RCHOHR, only have really a pair of oxidizable hydrogens, and so these are converted to ketones, because once we get to the ketone stage, there are no more hydrogens to remove from the carbonyl functionality. And of course, because many of these oxidations go through an aldehyde intermediate, strong oxidations of aldehydes also convert them into carboxylic acids. The general principle here is that the carbonyl compound goes as far up the oxidation ladder as it can without breaking CC bonds. For a primary alcohol like this, that means we go all the way to the carboxylic acid, and for a secondary alcohol like this, we get to the ketone stage. And the weak oxidations, which we'll look at in another video, also convert secondary alcohols into ketones in most cases. There are two types of reaction conditions that we see for strong oxidations very commonly, and the first that you see on the slide is based on chromium, and the second is based on manganese, permanganate. The top set of conditions are acidic. We see the inclusion of H3O+ in the reagents, and that's a good sign that the reaction conditions here are acidic. We'll look at the details on the next slide, but the essence of this process involves the formation of chromic acid, which is chromium with two double bonds to oxygen and two single bonds to hydroxyl groups. The exchange of the alcohol oxygen for one of the OH groups in chromic acid generates this chromate ester intermediate, which is really the key in oxidations by chromium. And the essence of this intermediate is that this extremely high oxidation state chromium, if you count it out, the oxidation number of chromium in this intermediate is +6, can act as a leaving group. It can accept a pair of electrons that lowers the oxidation number of chromium, and ultimately through elimination, which occurs within this organic fragment, we end up oxidizing the alcohol to a carbonyl compound. When we use manganese in the form of potassium permanganate, this compound, and sodium hydroxide, the conditions are now basic. But the essence of the idea is the same. We again have manganese in an extremely high oxidation state in this intermediate, and that manganese atom is dying to accept electrons. It can do so if it acts as a leaving group. And when elimination of one of these alcohol hydrogens occurs, that's exactly what can happen. Now, both of these eliminations would lead to aldehydes. Further oxidation of the aldehyde occurs spontaneously under both of these reaction conditions. That's why we call these strong oxidizing conditions, and that leads ultimately to a carboxylic acid. Now, the active oxidizing agent in oxidations involving chromium is chromic acid. It has the formula H2CrO4, and a Lewis structure is drawn here. If we look first at this intermediate, the thing we notice is that the oxidation state of the chromium is very high. We've got 1, 2, 3, 4, 5, 6 bonds to oxygen, which is much more electronegative than the chromium. This is chromium in the +6 oxidation state, and that's very high. There are a number of different ways to generate this intermediate. Most of them involve the combination of some chromate or dichromate source with acids. All of these conditions lead to the generation of chromic acid, and this is the active oxidizing agent, and so mechanistically they all converge to a common point. Chromic acid is a pretty strong acid thanks to all of the oxygen atoms linked to chromium. A good analogy for this actually is sulfuric acid. Imagine replacing the central chromium with sulfur. And so proton transfer from the chromic acid, acting as an acid, to the mildly basic oxygen of the alcohol hydroxyl group generates a protonated alcohol intermediate in the first step of this mechanism. The byproduct of this is something we might call the bichromate anion with an O- and the CrO3H fragment still intact. And in a primary alcohol situation, where departure of water as a leaving group isn't going to happen on its own because that would lead to a primary carbocation, we get an SN2 type displacement of water by this conjugate base. That's the second step of the mechanism. And at this point, we've really set up the key intermediate. This is the so-called chromate ester intermediate with an awesome leaving group in the form of high oxidation state chromium linked to the oxygen that was part of the original alcohol. This great leaving group acidifies the hydrogen linked to the alcohol carbon. In fact, that hydrogen is so acidic that a relatively weak base, something like water, can promote elimination of H and the CrO3H fragment. This gives an aldehyde product which is naturally oxidized with respect to the alcohol we started with. And this is the first stage of oxidation by chromium reagent. Notice that what we've essentially done from the organic starting materials perspective, from the alcohol's perspective, is the elimination of H2. We went from 2 hydrogens linked to this carbon and a hydrogen linked to oxygen to a product in which we're missing one of the hydrogens linked to the now carbonyl carbon, and we're missing the hydroxyl hydrogen. So H2, the elements of H2 anyway, have been eliminated. Now, under strong oxidizing conditions such as those involving chromium, aldehydes are oxidized spontaneously to carboxylic acids. And the mechanism of this oxidation is similar to the one we just saw, except that it's preceded by a nucleophilic addition. And we actually saw this in the general video on oxidations, that nucleophilic addition often accompanies these kind of substitution type oxidations of carbonyl compounds. We're under strongly acidic conditions, and so protonation of the aldehyde is something that can definitely occur. The most basic atom in the aldehyde is, of course, the oxygen, and that leads to this intermediate. And now water is around, and the nucleophilic addition of water to the aldehyde gives an intermediate in which we now have 2 carbon-oxygen single bonds linked to the carbonyl carbon rather than a carbon-oxygen double bond. And now proton transfer back to water, which is going to consume H2O and is going to generate H3O+, gets us to a neutral intermediate that can undergo further oxidation by the chromium. And this process as a whole, by the way, is called hydration. It's called hydration because if you look at what we've actually done, we've added the elements of water to the aldehyde. We have a new OH group linked to the carbonyl carbon, and we have a new hydrogen linked to the oxygen. And so on the whole, what we've done is hydration of the carbonyl group. We've added water to it. This intermediate we'll refer to as a hydrate, and we'll look at this mechanism in more detail when we talk about nucleophilic additions to carbonyl compounds in more detail in a future video series. The actual oxidation of the hydrate now proceeds very similarly to what we saw for the oxidation of an alcohol. After all, the hydrate looks a lot like an alcohol, right? If we can eliminate this H and this H from the hydrate, where we would end up at is a carboxylic acid. So I'm going to go ahead and draw that over here just to emphasize this point, that the carboxylic acid relative to the hydrate is just missing H linked to one of the oxygens and the H linked to the carbonyl carbon. Chromic acid is still the active oxidizing agent here, and so I'm going to draw out another equivalent of chromic acid, and this, being a strong acid, will protonate one of the hydroxyl oxygens. Now we've turned that OH2 plus group into a good leaving group, and so some kind of substitution mechanism can occur. Here I'm showing it as SN2. It could definitely occur via SN1 with the loss of water followed by coordination of this conjugate base to the carbon at the center. But through some kind of mechanism involving nucleophilic substitution, we arrive at a chromate ester intermediate where we now have a hydroxyl group linked to the carbon that bears the chromate ester. And if you recall what we just saw for the reactivity of a chromate ester derived from an alcohol, you probably know what's coming next. We have a good leaving group, the CrO3H group, positioned beta to a potentially acidic hydrogen. And so a base, such as water, relatively weak base again, because chromium is a great leaving group in this context, a weak base can promote elimination. This produces the carboxylic acid. It also produces H3O+, and a reduced form of chromium. So just to revisit this and summarize, we've eliminated 2 hydrogens from the starting hydrate. One of them ended up in this H2O that was lost in the substitution step, and the other one ended up part of H3O+, which formed after the deprotonation of this chromate ester intermediate. And this occurs spontaneously when we use most chromium reagents, strong chromium reagents that generate chromic acid, when we oxidize a primary alcohol. So the aldehyde is converted spontaneously all the way to the carboxylic acid.